Now, many of you have looked at this. I always post the preliminary notes. It's the notes from last how I taught the class. Get posted in Canvas first, and then update those during class. Repost them. So if you look at them for today, you'll see there's not much there.
Well, he made a record.
But I do have more to class today than just that. So a MATLAB demonstration based on material from last about Newton-Cotes rules. Basically, I'm going to show you why Newton-Cotes rules are only useful to a point, and we need to do something beyond that for more effective numerical integration. So Newton-Cotes, it seems promising conceptually, but is only a starting point.
Another diary?
Yes, because we're doing the MATLAB session. Okay. Well, before I actually do anything at the prompt, I'm going to show you the code that I'll be using. Now, I have a bit of a dilemma here because I can't show you all the code that I'll be using today because some of it is assigned as homework problems. But I will show you what I can, and at least I can explain the functions that you'll be writing later, even if I can't show you the code itself. So one file I can show you because I ended up for some reason not assigning. So this is from a homework problem, just not one that's assigned to you. So it's exploration 932. In this section, I've only assigned 931. I better check that, even though now it's on the screen and recorded, so you can it's given away forever. Okay. Yeah, I did not assign 932. Okay. So this is a function that computes the integral of a given function f on a given interval ab using an endpoint closed Newton-Cotes rule. So the fourth argument n is the number of quadrature nodes that you want. And remember from last time that by closed Newton-Cotes rules, one and include the endpoints AB among the nodes. All right. Now, so what we need is a vector of n equally spaced points in the interval AB that include the endpoints AB themselves. So the spacing between them is given by this, by dx here. So b minus a divided by n minus 1. So for example, if you wanted 4 nodes total, and including the endpoints, 4 nodes would leave 3 subintervals. So you want to take the width of the interval divided by 3 in that case to get the spacing. So that's what's being done here. Then I get a vector of all the nodes where I take the first node, which is A, and then I take the spacing times a vector of indices, 0 up to n minus 1. So this will give me a row vector consisting of A at the first element, B is the last element, and equally spaced interior nodes in between. This would have also done the trick, just calling lin space. You may remember lin space coming up in the very first homework. But I want to show you like how basically what lin space would do. Okay, once you have the nodes, then the nodes are passed to this function, and unfortunately, this exploration 9.2.4 that is assigned. But what it does, interpquad is short for interpolatory quadrature. So what it does is you pass along the same f, a, and b, and the nodes, and interpquad will take those nodes and compute the corresponding weights for interpolatory quadrature, which, as I showed you last time, are the integrals of Lagrange polynomials for the nodes. So that's really the main thing in interp quad. Well, interp quad delegates to a function that I've also assigned called interp weights. That computes the integrals of Lagrange polynomials. So then interp quad actually does very little on its own. It takes the nodes and the weights and evaluates f of the nodes, multiplies them by the weights, and adds them up. So it's actually not a very difficult function to write. Possibly. Or shouldn't be anyway, we'll see. So this function carries out triple story quadrature for whatever nodes you specify. The only thing unique to Newton cotes is those nodes have to be equally spaced. So I'm just making the nodes that I want, passing them on to do a triple story quadrature, and then y is my result. That's the approximate integral.
Do we need to type that in our diary?
I'm going to post this file, so there's really no need.
So what all are we doing in that diary?
I'm going to be calling this function. So you can be typing those into prompt if you want. Okay, but are there any questions about what this function is doing? I'm sure you're all reading a big cyber leaf, but I didn't sign this really complicated one. Okay, sure. Okay. Yeah, it's late.
I mean, you can still assign it if you want to. I'm sure we can all figure it out now.
Better. All right. I should mention that I was looking at the explanations that are assigned. Okay, so here's where all the homework problems are. Yeah, this one is so homework 7 is particularly MATLAB heavy. So you know. Now, because at some point you want to choose between all the homeworks and quizzes, which 2 assignments do you want dropped? I mean, we have everyone's toward the end, but so if you're particularly MATLAB phobic, there's a lot of functions right here, but each one by itself isn't too terrible. And really, the idea is you're building something. Like you have one function that delegates part of the work to other functions and so forth. Just like one you recently did, Lagrange fit, how that calls one function to make Lagrange polynomials, and Lagrange fit itself uses them. Okay. So now I'm going to use this function here. So I'm going to use Newton-Cotes quadrature for this integral of e to the x on the interval 0 to 1. Now, what I want to do is if I use Newton-Cotes rules for this integral, I want to compare the result to the exact answer. Now, what is the exact value of this integral? You all had Cal 2. I'm not expecting you to rattle off decimal places.
-1.
Yes, that. Yeah, so the exact result is, I'll say that the variable exact, so it's exp of 1 minus 1. Okay, so, I want to format long for this. Okay, so, for sake of a diary, I'll just read it. Okay.
Format long.
Okay, so that's what we're hoping for. Okay.
No format rats.
Although there's no point in if I now call this function quad Newton-Cotes. Now my arguments, the first argument is f.
Wait. why do you code?
Oh, you can't run it because you don't have a function.
Yeah.
Okay, hold on. I can, well, okay. I can put it in Canvas. Go. Oh, you know what? That still isn't gonna work. Even if I post that, that calls the function that's assigned. So unfortunately, you're not gonna be able to follow along in MATLAB yourself until you do the homework.
It's not, so it's not hands though?
I mean, I can post that file and I will, but even if you go ahead and if I post it here in Canvas and you go ahead and get it, that calls other functions that you won't have, and I should not post those because they're assigned for homework. So unfortunately, all you can do here in this MATLAB session is have to watch. So
Just watch.
I'm afraid so, yeah. But at least that way you won't have the stress of trying to follow along and get the commands right. And of course I'll post the diary.
Just have to watch and.
Okay, so I'm gonna call it, so what I have to pass as parameters are a function f by endpoints A and B and how many nodes I want. So in this case, whoops, I don't want that. I have @exp, where @ is used to indicate a function handle. So I'm passing the function exp as f, and then my endpoint 0 and 1. And then I'll just do a simple post rule. 3 nodes, that's actually Simpson's rule that we saw last time. Now, we don't really, in this case, we just want to judge accuracy. So there's no reason to just make it print out I and then you go ahead and visually compare decimal places. I can just do this. I can say error, and I'll compute the relative error. So that's an absolute value. So absolute value of the true integral, the approximate integral minus the exact, divided by the exact. So what's going to print out here is the error. So I'll go ahead and do that. Okay. All right, so this is Simpson's rule. Okay. All right, that's pretty good. So now I'm going to try again with more nodes. Because you would think the more nodes you use, the more accurate it should be. Let's put that to the test. Okay. Like if I try, let's say, 5 nodes. Okay, it is more accurate. Fine. Let's step up to 7. So in other words, you're fitting exponential with value 7 nodes. It's a 6-degree polynomial and integrating the polynomial exactly. Okay, yeah, all right. So our error is going to 0. Everything looks pretty hunky-dory. But then, if I go again with, let's see, what's the best that I can? Now, if I try 8, not much improvement there. And the error's not even cut in half. It seems a bit odd. Well, if I do 9, okay, so odd degree seems to be better. All right, so now we're getting pretty close to the unit round off. But let's keep going with odds. That seems to be going pretty well for us. And we're losing accuracy. Let's go up to 15. And it's going south all of a sudden. That's not good. Okay. Now, actually, what else? Try 20. MATLAB didn't like that. Give me a bunch of warnings. Let's take a look. Polynomial is badly conditioned. Add points to syntax. So what's happening is, because I'm using polyfit to construct a Lagrange polynomial, and okay, yeah. So my make Lagrange is calling polyfit, and so polyfit, as I mentioned before, sets up a van der Waals system to compute the coefficients of each interpolating polynomial in power form. And the van der Waals matrix is still conditioned in this case, so that's why it's freaking out. And sure enough, terrible accuracy, even though I'm using more nodes than before. Okay, so, and in fact, I'll just do one more. 50 nodes. Wait, actually, before I do that, I'm going to turn warnings off. I don't want those
Warning off.
I don't want those annoying messages again. And yeah,
It's messy.
Relative error should never, ever, ever be greater than 1, because if relative error is greater than 1, you might as well just have 0 for an approximation, because that would be better. So yeah, so that was pretty awful. What's kind of strange here is I have the diary from last time, when I talked about 2 years ago. It was same command, 50 nodes, and yeah, the error I got before was bad, but it was even worse, like order 10 to the 6. I'm not sure why it's better this time, even though it's still horrible. So go figure. Okay, so to shed some light on why we're losing accuracy as the number of nodes increases. I mean, at first we were gaining. We're going to take a look at quadrature weights. So I have a function for that, and I can't show you this function because it's assigned. It's homework. So interpret weights. So I'm going to get the Newton-Cotes rules. So I'll use linspace to generate them. So I'll just do for Simpson's rule first. So here are the nodes. That's the first argument it takes, and then the endpoints, 0 and 1. And interpret weights will return a row vector, which I don't want. I want a column vector. So I'm going to transpose the result. All right. So here are the weights. Now, this is actually something we've seen before. Remember I told you about Simpson's rule? There are 3 nodes, therefore 3 weights. What are the weights? B minus A over 6, and then B minus A times 4 over 6, and then 1/6 again. So sure enough, for interval 0, 1, we have 1/6, 2/3, 1/6. How the node in the center, the midpoint, gets 4 times the weight of the endpoints. So these are the weights that we would expect for Simpson's rule. So then if I increase the number of nodes, there's a certain symmetry to the weights. Now, as far as when things started to go badly, let's look back. There was some degradation by the time we got to 15, or even 11. 11 nodes, we were losing some accuracy. Let's take a look at that case. So what are the weights like when we have 11 negative weights? That's why accuracy suffers. So once the weights go negative, it's game over. You should definitely not use that quadrature rule. I'm going to backtrack a bit. When did they first go bad? How many nodes did it take? So 10 nodes. Okay, those were all positive. 9. There's some negative weights at 9. And then at 8. Okay. So it looks like 9 nodes, for at least for a closed Newton-Cotes rule, has negative weights. It's been proven that for n greater or equal to 11, every Newton-Cotes rule, open or closed, will have at least 1 negative weight. Interesting proof. I wonder how I prove that. Okay, so any questions about what's going on with these weights?
Watch it follow along instead of trying to keep up, like I don't have the code.
Unfortunately, yes. Printout doesn't number the pages, which is kind of aggravating. Okay. So in this case, so we see here why high degree Newton-Cotes rules are not a good idea. Now, what might be better than using equally spaced?
Championship.
Yeah, because we see that Chebyshev helps for polynomial interpolation. And I showed in Runke's example, it did help. So let's try that. And I mentioned using Chebyshev points for quadrature last time, very briefly. Clenshaw-Curtis quadrature uses the Chebyshev points as nodes. Okay. So we're going to look at So if we have 10 nodes, so in other words, the degree 9 interpolant, but the Chebyshev polynomial, its roots. Okay, so XC, the Chebyshev points. I'll just use the formula for them. This would have come up in homework 5. I transpose it because I like column vectors. Times pi over 2n. Okay, here's the formula for Chebyshev points, but what I need to do to them, because these are for the interval -1 to 1, but I'm not integrating on -1 to 1, I'm integrating on 0 to 1. So what I need to do is shift them up by 1, and then divide by 2. Okay. So, I need to set n equal 10. Whoops. Okay, so here are the Chebyshev points mapped to the interval 0 to 1. Notice in the middle of the interval, so around 1/2, there's a fair gap between them, like 0.15 between this one, this one, this one. But as you get closer, the quadrilaterals get much closer together. But we already knew that about Chebyshev points. They're clustered near the boundaries. Okay. So now I'll call this function that's assigned for homework, as I mentioned earlier, interpquad, exponential from 0 to 1, and I'll specify these Chebyshev points as the nodes. Now compute the relative error like before. Okay, and let's see how this does. Okay, pretty good. I'm as good as my previous diary, so that's kind of strange. Okay, but now I'll ratchet it up to 20. Okay, and then I'll compute the nodes again, Chebyshev points, and try interpolatory quadrature again. And that didn't go so well. So this is a little unsettling. Oh, not for me, I knew it was going to happen, but or maybe not be unsettling for you because you don't care. But it's not what you would expect based on what I told you earlier. But with Chebyshev points, you're supposed to get positive weights. So this loss of accuracy as number of nodes increases shouldn't be happening. Okay. And if I were to go further, that would be so let's take a look at the weights in this case. Integral weights, XC on 0 to 1. Okay. Well, they are positive, so we don't have an issue with negative weights in this case. So So we don't have that explanation for the loss of accuracy. Okay. Now, okay. But I can give you an idea anyway as to why this isn't going well. Because of how the weights are computed. Because this function that I just used, interpret weights, what it does is it forms Lagrange polynomials for these points, and then it computes the integrals of those Lagrange polynomials using MATLAB's functions. Because MATLAB has functions polydir and polyint that compute derivatives and integrals of polynomials respectively, just because it computes the coefficients of a derivative and the antiderivative. So you can use that to compute what should be the exact integral of a polynomial, except for rounding error. But what I'm going to do is I'm going to compute one of these Lagrange polynomials and show you the coefficients. So, okay. Now, Lagrange polynomials, as you know, here I have 20 points. So in this case, Lagrange polynomials would be degree 19, one less. And each Lagrange polynomial is equal to 0 at all the interpolation points, except for one of them where it's equal to 1. So what I need is, I need a vector of y values that are all 0, except one of them is equal to 1. So I'm going to create a 20 by 20 identity matrix. And then what I'll do is, to get my y values, I'm going to choose an arbitrary row of this matrix. All right, so this vector is all zeros except in the 15th position, there's a 1. Now what I can do is compute the coefficients of a polynomial that interpolates at these points, the Chebyshev points, with these y values, and the degree would be 1 less than the length of the number of xi's you have. Okay. Now this is going to spit out a row vector of coefficients, but for visual purposes, I'm going to transpose it to get a column vector. Let's see what the coefficients of this polynomial degree 19 look like. I have no idea what this is going to look like, but I can speculate. And my speculation was right. Notice they vary widely in magnitude, all the way up to 10 to the 12th. When you have polynomial coefficients that vary this widely in magnitude, you go to evaluate this polynomial, especially these power form coefficients, you run the risk of because the values of this polynomial are 0 at most of these points except 0 or 1. So evaluating the polynomial in power form using these coefficients would lead to catastrophic cancellation. So what that means is I cannot assume that these quadrature weights shown here, they are positive, so that's nice, but they're not necessarily computed accurately. So, in other words, by calling this function right here to carry out interpolatory quadrature using a Chebyshev points, technically, I was carrying out what is known as Clem-Shaw-Curtis quadrature. However, this was a lousy implementation of it because it did not compute the quadrature weights in a numerically stable way. The reason being that what the code does is it computes these polynomials in power form like this one, and then uses like polyint and polyval to obtain the integral of the Lagrange polynomials over the interval AB to get the interpolatory quadrature weights. And because these coefficients are so haywire and very widely magnitude, there's too much round-off error occur. So, but there's actually a I'm not 1000% positive about this, but it's been many years since I've actually studied dimensional curves quadrature or taught about it in a class. But I'm pretty sure there's an analytical formula for the weights. So a proper implementation would use that instead. So a lot of times, and this is the issue with numerical methods in general. You can have everything worked out on paper and say, oh, okay, this is what I need. If I can go code something in MATLAB and have what I want, and you try it out, and it goes very badly because you weren't thinking about things like rounding error, catastrophic cancellation.
It becomes a disaster.
It can happen, yeah. So, and that's why you have to be careful about how the formulas you work out on paper are coded up to avoid these kinds of issues. Like for example, you may not necessarily have taken like a second linear algebra class, but in a second linear algebra class, such as our own, Math 426, one of the things that's taught is called Graham-Schmidt orthogonalization, also mentioned in certain classes like Math 415. So you have a bunch of vectors that are non-orthogonal, you apply Graham-Schmidt orthogonalization to them, and they become orthogonal. And so that's taught in a lot of linear algebra classes, and it's fairly straightforward and tedious procedure. And then you take a numerical linear algebra class, and you find that that's the worst method possible for a computer to make vectors orthogonal. And then, so in class like Math 610 for graduate students, I teach about better approaches than that. So that's that gap or even a gulf between what happens in math courses that teach analytical methods versus numerical ones. And something inherently wrong with the analytical ones. But when using those analytical methods on a computer, you have to be careful. Okay, and that concludes this MATLAB demonstration.
Diary off.
Okay, so any questions about what happened here? It was a disaster of numerical integration.
Disaster.
Okay, now that I've shown why you have to be careful with interpolatory quadrature, I'm going to show you an alternative that still makes use of interpolatory quadrature, just more judiciously. That's the subject of today in these brief notes on composite numerical integration rules. Because last time I derived a few error formulas for Newton-Cotes rules, or at least showed you what the error formulas were for midpoint rule, trapezoidal rule, Simpson's rule, and all of the error formulas had a power of b minus a in them. What if the interval AB is large? Then you can incur large error for that reason. Or if higher order derivatives of f are large, and that could be a problem too. So the idea behind composite rules is you take your interval AB that you're integrating over, you divide it into subintervals of equal width, so b minus a over n, we'll call that h. And then on each of those subintervals, you use a quadrature rule such as Simpson's rule or trapezoidal rule. Because in that case, what you saw before about the error formula having a power of b minus a, like b minus a cubed or b minus a to the fifth, that's a liability if the interval AB is large. But now if you're cutting AB into small subintervals of width h, that liability now becomes an asset. So now I will show you composite versions of the three Newton-Cotes rules that I showed you last time. All right. So for all of these, we divide the n subintervals. This is the width, b minus a over n. And each subinterval has these endpoints. So I define these x values are equally spaced. So x naught is equal to a and xn is equal to b. I have n subintervals of these endpoints. So then, from a midpoint rule, really what I'm doing is I'm considering pairs of subintervals and using a midpoint of each. So really what we have here is n over 2 subintervals, each has width 2h. So the first subinterval, the endpoints are x0 and x2. The midpoint of that is x1. So that's where I'll evaluate f. Second subinterval, we go from x2 to x4. The midpoint is x3. That's get plugged into f. And then I add all these up. So I only have to evaluate f like n over 2 times. We're assuming here that n is even. Now, all right, so that's a composite midpoint rule. Now I want the error. Now, this expression right here, this is from last time, that's the error formula for the basic midpoint rule. That just evaluates the midpoint. So now what I do here is, okay. I've divided AB into basically n over 2 applications of the midpoint rule. So I take the error from each one of these and add them up. So for each application of the midpoint rule, I'll have this expression where I'm applying the midpoint rule on an interval of width 2h. That's what goes down here. So wherever you see b minus a here, that's going to be 2h here. And each time we have the second derivative evaluated at a different unknown point within its own subinterval. So now I add all these up. After I work out the constants, I can pull out h cubed over 3. And now I'm adding up all of these. And by the intermediate value theorem, adding up these n over 2 values of the second derivative is equal to n over 2 times the value of some of that second derivative at some unknown point in between them. And this is true provided that the second derivative is continuous on AB. So now, once I simplify all of this, and keep in mind I'm using a simplification that n times h is equal to b minus a. So this is my overall error formula. So second derivative unknown point over 6 times b minus a, then times h squared. So because the error is proportional to h squared, that's the order of accuracy. We say that this rule is second order accurate. Any questions about where the error is? So it really is taking the error from the corresponding Newton-Cotes rule, applied on subintervals and adding them up. Now, here the midpoint rule is written in a rather unconventional way because normally we think in terms of having n nodes to evaluate at n nodes, but here I'm defining n plus 1 points, and I'm only using every other one. So a more conventional way to write the composite midpoint rule is down here, that I'm approximating the integral by h times the sum of these f values, where now I have n subintervals, each of width h, and this is the midpoint of each one of them. So I add all those up, So then that changes the error formula a little bit. The constant. So now you have 24 instead of 6. And it's because the width of the subintervals is cut in half. And this method is order h squared. So this is a more conventional writing of the midpoint rule and its error. Because the other rules I'm going to show you, they also evaluate at n or n plus 1 points. So we want to compare apples to apples in terms of because how many times we evaluate f, that's how you measure the computational expense of these rules. You want to reduce the number of evaluations of f. So at least all the rules I'll show you evaluate f pretty much the same number of times. Here's a composite trapezoidal rule that comes from evaluating, applying the trapezoidal rule to subintervals, again, with h. Now watch what happens here. I'm evaluating f at all my points, x0, x1, x2, up to xn. But notice all the ones in the middle, in the interior, have twice the weight of the ones at the endpoint. Now the reason for that is, if I'm applying a trapezoidal rule on each subinterval, the first trapezoid will involve f of x0 and f of x1. The second trapezoid will involve f of x1, f of x2. F of x1 is shared by two trapezoids. In fact, all of these f values are shared, each of them shared between two neighboring trapezoids. Whereas the f values at the endpoints, each of them is only involved in one trapezoid. So that's why the ones in the interior have twice the weight. And each trapezoid has width h. And the 1/2 here comes from the formula for the area of a trapezoid, because we're taking the average height. And this is another way of writing the composite trapezoidal rule using a summation. Sometimes this rule is taught in Cal 2. Just depends on whether the instructor selects that topic. Generally, calculus textbooks have a section on approximate integration. And as a numerical analysis person, I get offended when they just call it the trapezoidal rule. It's like, it's a composite one, you do this. Yeah. Anyway. And maybe this is why I haven't taught Cal 2 since 2012, because I wouldn't back about it. Okay. And finally, composite Simpson's rule. Now remember, the regular Simpson's rule, you evaluated f at a, b, and midpoint, and you had coefficients of like 1, 6, 4, 6, and 1, 6. But once again, so really what I'm doing is I'm applying Simpson's rule on pairs of subintervals of width h. So really I'm applying it on an interval of width 2h. And this f value is shared between two adjacent applications of Simpson's rule. So that's why the weights are 1, 4, 2, 4, 2, 4, 2, and so on, from adding up all those applications of Simpson's rule. And the way this is written, this requires that the number of subintervals must be even, because you're applying Simpson's rule on pairs of subintervals of width h. All right, so that's the statement of rule. So you can compare this to the composite trapezoidal rule. It's the same amount of computational expense. It's just that each evaluation of f is multiplied by a different weight. And generally, Simpson's rule is more accurate. So this is the error formula. It's fourth order accurate compared to the midpoint and trapezoidal rules. Oh, I do not have the error for trapezoidal rule here. Where did it go? Oh, I derive it later. Yes, I haven't listened to those in 2 years. Shut up. You would, you're thinking it. Okay. So midpoint rule will seem to be second order accurate, Simpson's rule, fourth order accurate. But it involves a higher order derivative of that because of that higher order accuracy. So now I'm going to take the time to derive the error formula for composite trapezoidal rule. So what we have here, what's being summed up is the error in the regular Newton Cotes trapezoidal rule. And that's being summed over n subintervals. Each subinterval has width h, so that's why we have h cubed. Because the error formula for the Newton Cotes trapezoidal rule had a factor of b minus a cubed in it, so now h cubed. Each time we're evaluating the second derivative at an unknown point, a different unknown point. So then what I do is I go ahead and pull out constants, h cubed and 12. I mean, I multiply by n over n, which seems odd, but what I do here is I take the n in the denominator and I associate it with the summation. And I take the n in the numerator and I multiply it by one of the h's. So I'm using the fact that n times h is equal to b minus a. This here is an average of f double prime values. So like before, I'm using the fact that if I assume that f double prime is continuous on AB, then I can apply the intermediate value theorem and conclude that there's some point eta in AB such that f double prime at that point eta is equal to the average of these other f double prime values at points in AB. So that's one of the nice uses that we've seen a few times of the intermediate value theorem. But if you have a continuous function on interval AB, the intermediate value theorem tells you that at some point in AB, the function is equal to either an average or weighted average of function values also taken from AB. Oh, that didn't notice. Wow, wait, really? Yeah. Okay. So here we get the error formula, but actually I'm not entirely done yet. Because I do want to show you this example of how these error formulas that I've shown you can be applied. Okay. So this example, oh look, it's the same integral I was doing earlier, e to the x, from 0 to 1. Also, some convenient example. Okay. Now my goal is to use a composite quadrature rule to get error less than 10 to the minus 3. So if I would ensure at least 3 decimal places correct. So what I'm going to do is I'm going to use the error formula first for a trapezoidal rule and set the error less than 10 to the minus 3 and try to solve for a value of n. That would make the error that small. Okay, so here's the error formula that I just derived for a composite trapezoidal rule. Now my function is, my integrand is e to the x. So the second derivative will be e to the eta. And then I'm using the fact that h is equal to b minus a over n. So once I take that into account here, then and also the fact that a is equal to 0 and b is equal to 1, my expression for the error simplifies to this. Now, eta is an unknown point between 0 and 1, but the exponential function is increasing. So the largest that this can be is e to the first, so in other words, e. So now I can say that the absolute value of the error is bounded by e over 12n squared. So now I set that less than 10 to the minus 3, and then I solve for n. And this is what I get. So as long as I use at least n equals 16, I have a guarantee that the error in the composite trapezoidal rule will be less than 10 to the minus 3. Any questions about how that number of subintervals was obtained? I do the same thing with Simpson's rule, same idea. So once again, I simplify the error, I get this. And well, the error would be less than 10 to the minus 3. So when I solve for n in this case, I get 1.9. So in other words, n equals 2 is fine. And so in fact, I don't even need composite Simpson's rule. I can just use regular Simpson's rule. And that's what I do down here, knowing that the error is going to be small enough. And this is what I get, 1.71886. And the exact value to 5 decimal places is 1.71828. So the error is 0.00058. So the error really is less than 10 to the minus 3. So it worked out. The error formula tends to be pretty conservative, so you're going to get like an overestimate of how many intervals you need, because whatever higher order derivative appears in the error formula, we're going to take its maximum. So the error is exactly equal to this for some point in here. We have no idea about it, but just to be on the safe side, we find where that derivative is maxed. Okay. So this is one use of error formulas, is that you get an idea of how much computational expense you need to incur to get the accuracy that you're looking for. And that's why we spend so much time on error analysis. Okay. Well, we're only having 2 pages of notes, so I built this time pretty well. But I just remember every time before class, I need to look at this, like the schedule from last time. Like, did I do a math demonstration 2 years ago? Like, oh, dang it, I did. Okay. Are there any homework issues? Okay. It's not like a pretty crummy weekend, but that sounds like a pretty crummy weekend.
Well, that and you.
Oh. Okay then.
It says like this thing's that you're assigned for your class.
Yeah, but when you can come close with
9.6.
From our standpoint.